podium over to our chair who will conduct this session.
Let me just say that there's 5 more slots or so.
Five.
Something like that. Approximately, plus one. So you're most welcome to come and tell me.
Very pleased to be chair of this session, and essentially Yakir Aharonov is responsible that I'm here. So let's tell Yakir Aharonov what quantum mechanics is. It will do 10 minutes before the end.
Okay. Thank you. As you know, my research, could you hear me well?
Yes.
My research was always on the foundation of quantum mechanics. And from the beginning of my research, I tried to follow the following idea. You know that the most surprising thing about quantum mechanics is the fact that 2 identical systems behave differently in the future. 2 atoms that are completely identical, they are exactly in the same surrounding. One of them may decay after 1 minute and the other after 1 hour, and there was absolutely no difference between them. That is really preposterous. That's the thing that led Einstein to declare that he will never believe quantum mechanics because he doesn't believe that God plays dice. I was guided in my research from the beginning by a rephrasing of this statement of Einstein, and I asked myself, why does God play dice? Namely, I was sure that there is some positive reason for this kind of uncertainty, something that nature gains from it. It's not just making something negative without something important that is gained by it. And I want to show you today that, led by this idea, I came to realize that it's possible to reformulate quantum mechanics in a new way, and the essential new way is the fact that 2 particles that are the same at the initial time, there is already now difference between them, but we will discover this difference only by a future experiment. So I want to show you that it's possible to reformulate quantum mechanics by using, at each moment of time, 2 vectors in Hilbert space to describe the system. In fact, 1 ket and 1 bra. One vector comes to the present from a past experiment, and the other vector comes back from the future from some future experiment that we will do in the system. And both of them, on equal footing, describe the present. At first sight, when you hear this, you might think that is crazy, because if anything that the future vector can affect the present, we will do the experiment in the present, then wait for the future and change our mind and make a different experiment in the future. So what's going on? So I will show you that the uncertainties of quantum mechanics are exactly the minimum one that are necessary in order to allow this reality to be consistent with free will. So God plays dice in order that the future could play a role in the present and not only in the past, and nevertheless it doesn't violate causality. We have free will, and this is due to the fact that the uncertainty principles are exactly the ones that allow all this to happen. So that to me is the reason why God plays dice. Now, when I tell you that it's possible to reformulate quantum mechanics this way, I'm not going to tell you that it's good to do this only because of this philosophical reason. It turns out that when you reformulate quantum this way and start to look at it at different examples by using this 2 vector picture, you suddenly uncover a host of new phenomena and new concepts that were there all the time. After all, what I'm doing is nothing more than just reformulation, so obviously the same prediction that this formalism gives is the same prediction as the old one. But because of this new way of looking, suddenly we can find inside quantum mechanics completely new features that we did not suspect, very rich ones. Once we find them, we can go back and use the old formalism and see exactly the same results. But we could have never guessed it if we did not use the new formulation. Okay, this is the introduction. I hope that this will make most of you awake for at least a while more. And let me now show you how this works. So the fact that in quantum mechanics two particles behave differently at a later time allow us to do in quantum mechanics something that we can never do in classical physics. We can define in quantum mechanics something that I call pre- and post-selected ensemble. Ensemble that is not only defined if this is time. In a time t1, I choose lots and lots of particles that all have the same initial state, etc. I can still do a second experiment in the future, and if I do a measurement that doesn't exactly check this state, but checks some other variable, then I will find that this one will have one value, one state, this one with another state, so then I can select the sum number of particles in this ensemble that all end up in the same final state and call this pre- and post-selected ensemble. If you want to think about a concrete experiment, suppose I have a cloud chamber. Those of you that are young ones don't know that once elementary particle experiments were done not by counters, they had to rely only on cosmic rays, and they were using cloud chamber. Cloud chamber is a chamber that has overheated or subcooled gas that the minute when a particle comes by, it leaves a trace of bubbles, okay, and goes out. So now we can send one particle after the other. All of them start in the same state, essentially a state that has zero momentum in this direction and some momentum in this direction, and take a record of each one of them and keep all the tracks, all the records of the tracks, but then look only at the records of those particles that finally ended in this computer, in this detector. We discard all the tracks that came out from particles that ended up in these other detectors. That's why it's called exclusive experiment, because we exclude all these results. Now, I could never do such an experiment classically, because classically, if I send one after the other particles that are exactly in the same state, and if this starts in the same state also, all the particles will always go to the same detector. So once you know exactly the initial state of a classical particle and you enter it with the same measuring device, you will always end in the same state finally. So you can't do this pre- and post-selection on classical particles, but you can do this pre- and post-selection on quantum particles, and I call this pre- and post-selected ensembles. And let us see now what are the properties of this kind of tracks that belong to the sub-ensemble, the pre- and post-selected one. So now I pose the following question. I start with particles that all of them started with initial state psi1. I post-select only particles that ended up in the state psi2. And then I ask the question, what happens if at the present, between the two times, I will make a measurement of some observable that is described by emission operator A, and I have a complete set of eigenstates, A times A is equal to A times A. So the type of question I want to ask, what is the probability to start with psi1, in the middle finding the state AN, and then finally finding the state psi2? How many times I will find A1, how many times I will find A2, but because I select only a part of the particles, the number of times I will find AN is not dictated only by psi1, it depends also on psi2. So let's see how is this dependent. So I will first use the usual picture, the conventional one, which just uses at any time one vector. So according to the usual picture, I have here a time evolution for a given Hamiltonian of psi1 of t. So psi1 of t is the wave function started here as psi1, evolves until the intermediate time t. And then I make a measurement and find a particular result which is AN. Then I must start from here with a new state, which is an of t. I propagate this state up to the final time, and then I postulate that thing. So from now on I will have another state which will be psi2 of t. So according to the usual picture, I have always just one vector propagating from here to here, another vector propagating from here to here, and a third vector propagating further. And I ask now the question, what is the probability to find a particular an under this condition? And everybody knows how to calculate it. I take psi1 multiplied by the time evolution operator u of t1t. Then propagate the state psi1 to the time t. Then take the scalar product with an. I think I'm too close to the loudspeaker here. So, I take psi1, propagate it from the initial time to the intermediate time t, take the scalar product with an, then propagate an from the intermediate time t to the final time t2, project it on the state psi2, and if I call this Cn, then absolute value of Cn squared is equal to probability to start with psi1, in the middle getting an, and then start with an and getting psi2 at the end. Okay? And then if I do the calculation for all values of an, I will get the probability, relative probability to get all the answers. Of course, if I sum all of this, I will not get 1 because I've excluded some of the results from the original ensemble. But now I do something that is trivial in mathematics, but it has very, very far-reaching consequences in physics. I take this u and bring it here, and do the same calculation by having here u daga of t 2t an. Sorry, psi2. Psi2 an u psi1. This gives me exactly the same value Cn. So I certainly am allowed to say that I will do all my calculation using this picture. But this picture is a very interesting one. It tells me that instead of looking in the conventional way, this picture suggests that I will take psi1, propagate it up to here. I will take psi2 and propagate it back in time until the present, because u daga is the time evolution in the opposite direction. And I will use both vectors on equal footing to calculate the probabilities here. Since it gives me exactly the same prediction as normal quantum mechanics, I'm allowed to use this way of looking at quantum mechanics and see where it leads me. So far, of course, it gives me exactly the same prediction, but it will lead me to something completely new when I think about it before I look at results of experiments, but to think about some actual reality that exists independent of what I measure. That is the idea. Let me just mention briefly that using this picture already now has a fantastic advantage mathematically. It simplifies the calculation enormously, because if I use the one vector picture, each time I have to start with another an, I have to solve another differential equation to propagate it from here to the future. Here, one thing for all, I use one differential equation to calculate that, another differential calculation to calculate that, and then from now on I will use only products of vectors. This is a fantastic simplification. That will be ample for any different experiment to be done here, or different times where I do the experiment. So in fact, I simplify infinitely the calculation if I use the two vectors rather than one. Already this is an advantage, but if this were the only advantage, I wouldn't waste your time. There is much more interesting advantage than this one, but it's nice to remember already this one. Now, I come to the idea that contrary to what usually people tell you, that we should worry only about the results of experiments and never try to ask the question, what is there in the quantum domain, even if we don't do an experiment? Can we give a meaning to what's happening there that is independent of the kind of experiment which we are going to do? Now, the whole doctrine of Bohr and Heisenberg and everybody, even today, everybody feels that in fact it's not fair to demand a physical theory to describe what is a reality, especially in the microscopic domain. The only purpose of a physical theory is to give predictions for results. In fact, there was quite well-known physicist, Arthur Perez, who died a few years ago, and he said that he would like to have on his tomb, the statement saying that non-performing experiments have no answer. You should never try to consider what happens in the quantum domain before you say what experiment you will do, and only then hope to get some answer. That's the thing that made Einstein so unhappy about it, because we believe that there is a true reality in the quantum domain. I believe so too, and you will see that believing that leads you to some really interesting new questions. So let us look now at the two-vector picture, and let us take the simplest quantum system, which is a spin-half system, and we start with a time c1 with sigma x equal to +1. At time t2, we find that sigma y equal to +1. We also believe that there is no magnetic field, so both spins are constants of motion, both components are constants of motion. This is time. And now our new picture tells us that it's true that both sigma x was equal to 1 all the time and sigma y was equal to 1 all the time. What's going on here? We already know for sure that if we know sigma x, we are not allowed to know sigma y. That is the whole meaning of the uncertainty principle. And here suddenly I am trying to tell you that this single particle at a given time has both sigma x equal to 1 and sigma y equal to 1. What's going on? Do I break the whole holy principle of uncertainties? Well, let's see if we try to follow what is this trying to tell us. Well, there is a simple experiment you can do that checks if sigma x equal to 1 and sigma y equal to 1 by doing the following. You first measure sigma x, then you measure sigma y, and you know that you will get here sigma x equal to +1 because this must agree with that answer, since the spin was conserved. And you know that sigma y is equal to +1 because that must agree with this one. But very quickly you realize that's a trivial statement, because we know that here we could have written in half the cases +1 and half the cases -1, but we simply decided to discard all the cases -1 because we are going to keep only those one at the end. So there's nothing interesting about saying this equal to +1, this equal to +1 here. We did not say anything new. What happens if we measure in the opposite direction? If we measure in the opposite direction, first sigma y and then sigma x. Of course, we will get here 1 and 1, because making a measurement here of sigma y will destroy sigma x, and therefore if afterward we follow with the measurement of sigma x, we will get 1, can get 1 or -1. So this certainly is not a way to check that both of them are there, because we disturb both of them when we do this. So I was looking for a new kind of experiment that will be able to show me that both things are there. A new kind of experiment. This new kind of experiment must be an experiment that hopefully doesn't disturb any of the vectors. So I asked myself, suppose I try to look at the measurement of sigma x plus sigma y. Will I get the answer 2? At first you look at it, you say, you're crazy, how can you get the answer 2? If I divide by square root of 2 here, you will get the square root of 2, but I know that this object is without spin in the component in the 45 degrees, it can be 1 or -1, it can never be square root of 2. So in no way can you hope that if we measure sigma x plus sigma y, you will get the value 2, or the spin component will get the value square root of 3 and 1. Now when I looked at that, I didn't want to give up. I said there must be some sense in which I should be able to get this answer. I was stubborn. And then it occurred to me that if I could find a new kind of measurement that will give me information about the system and nevertheless will not disturb it, then I will be in business, because that information will be able to know that this vector exists and that vector exists, and therefore the sum must give me 2. So here I show you what kind of new measurement I thought about. The name that finally I gave to this new measurement is weak measurement. And the idea is the following. Suppose we look again on this very simple quantum system, but instead of having just one spin, we have many, many spins. And somebody told me, they are not interacting, somebody told me, look, I prepared all these spins in the same direction. This is the direction where all of them is equal to +1. He asked me, you have this large number of spins in that direction. Can you find the direction of these spins without at all changing any of them? Now, as long as the number of spins is finite, you can prove that that is impossible, because if you look at the vector which is the product of this one, and you look at the vector which is the product of the same spins in some other direction, that product, scalar product, is usually not equal to 0, because the product of this one times that one is some cosine of an angle, so the product of all of these bands times that one will be cosine of this angle to the power n. But if n goes to infinite, if we have a true ensemble or n sufficiently large so that this is sufficiently close to 0, then we can even hope that we can measure this without disturbing it. Because there must be some kind of an Hermitian operator for which this one has one eigenvalue and this one has another eigenvalue at the limit when n goes to infinite. So that led me to the idea that perhaps there is a way at that limit to do something very interesting. Usually we assume, by all the things that we were taught, that when we want to find information about quantum systems, we must disturb it. The more information, the more disturbance. If we want no disturbance at all, there is no information. Now I want to show you there is a very interesting limit in which, if you have many, many particles, if the amount of information that you want to get from each particle is epsilon, very small, then you can show that the disturbance of this system will go like epsilon squared. Therefore, you can show that if you have large enough n particles, you can find meaningful information if all of them are in the same state. Because if each one of them give information which is lambda over n, and lambda is larger than 1, then from all of them together you will get information, because you will get something larger than 1. But if the disturbance goes as the square of that, lambda squared times n squared, then you multiply it by n, that goes to 0. So that means that there is a true limit, very interesting limit in quantum mechanics, like safety in numbers, that by reducing the disturbance of each one of the system enough, you can measure something and no disturbing. So the usual doctrine that you are not allowed in quantum mechanics to get information without disturbance is absolutely wrong. So this is the concept of weak measurement. The weak measurements are such that you've reduced the disturbance so much that you can forget about the disturbance and still be left with information. This will be the last proof I will give you, because then I have to go a little bit faster to show you how many interesting things you can get. But I wanted at least to show you the proof of this work. 50 minutes is not enough to show you a whole new development. So I will do as much as I can. Okay, so suppose suppose I have an ensemble of particles that are all in the same state. So the state of the ensemble is the product over n going from 1 to n times states for particle n, and all the states are equal to each other. And the question is now, at the limit when n goes to infinite, can I find what is the state of each one of these particles without disturbing any of them? So for example, if each one of them is some function of x, can I find this function? Can I find this wave function without disturbing even one of the particles if I have a large number of them? This looks like the opposite of what everybody tells you. Everybody tells you in order to measure the wave function, you have to do statistical experiment, how many particles you find at x1, how many particles you find at x2. I'm going in exactly orthogonal direction to that. Because in that direction you can't say that this psi of x has any real meaning because you disturb it. But I want to say that when you go to the limit, when n goes to infinite, there is a true, real property of this ensemble of particles that is really there because you can look at it, you can observe it, you don't disturb it. It is a true property of this ensemble of particles. Because per definition, because you can measure something without disturbing it, it's really there. Okay. And you can repeat the experiment more and more times and you always see that it's there. Okay, so what do I do? I want first of all to give you just one very simple theorem that I always found it extremely surprising that you don't see in any quantum book. If you look at the following question, you take any Hermitian operator and multiply by any vector in any Hilbert space, you can always write this as A1 times psi plus A2 times some state which is orthogonal to psi. That's a trivial geometrical statement. A times psi gives you a new vector. You take this new vector, ask what part of it is in parallel to psi and what part of it is orthogonal to psi. You can always do it like that. And you can immediately show that you can make this A2 real because if it's complex, you can take its phase and bring it to the definition of psi because the phase of this psi is defined. So we can assume later that A2 is real. Okay, let me show you what is A1 and A2 is. I will tell you the answer. A1 is equal to what we call A average, and A2 is equal to what we call the uncertainty of A, where A average and uncertainty of A are the statistical properties connected with the state psi. A average is the average of A statistically in psi, and the delta A is the uncertainty of A in psi. Now what's surprising is this is a statement about a single vector, which has nothing to do with statistics, and nevertheless it's there already that we see those numbers that are later connected with statistics. How do I prove it? Well, it's very simple. If I multiply this by psi, psi times psi gives me 1, times psi orthogonal gives me 0, so I just get A1. So I already know that A1 is the average of A. Now I multiply the vector by itself. So I take the vector A psi and multiply by the vector A psi. And look what happened in the other side. On the other side I get A average square plus A2 square. Now, since this is a Hermitian operator, this is equal to psi A square psi, which is equal to the average of the square of A. So indeed I see that A2 square is equal to the average of A square minus the square of the average of A, which is delta A square. So I have this beautiful general theorem in quantum mechanics that should be in any quantum book, which says that if you take any vector and any psi, you can always write it as A average times psi plus delta A times some orthogonal state to psi. That's true in any Hilbert space in any number of dimensions. Okay, I leave it now as a home exercise to prove, because I have to go quickly now to show you some interesting new answer, to prove that if you take the sum of an divided by n and multiply by the ensemble, psi total is the ensemble that I wrote before, that this is equal to A average, the individual average for one particle, times the ensemble state, plus delta psi, where delta psi, the scalar product of delta psi times delta psi, goes to 0 as 1 over n. So that means that I've shown to you that it's possible to measure, to find the average of any operator A if you have enough particles without disturbing any of them. So in particular, I can measure the projection operator in any position by looking at the sum of pi n divided by n on that projection and find what is psi star psi at any position. And similarly I can do with another projection that will give me also the phase. So in principle, if I have enough particles, I can find a measurement that I call weak measurement that will measure the state of each one of them, provided I know they are all in the same state, will measure the state of each one of them without disturbing it. So this is not a measurement that produces state, but it is a measurement that can check. If somebody tells you that I have many particles that are in the same state, you can check that statement without disturbance at all. And now I very quickly start to show you what are dramatic answers by learning to use this kind of weak measurement. So first of all, if I look again on a state where I had sigma x equal to plus 1 initially and sigma y equal to plus 1 finally, if instead of now having just one case like this, suppose I have many replicas. Suppose I have now a large number of particles that are all have the property of sigma x equal to plus 1 at the beginning and sigma y equal to plus 1 at the end. Then the answer is I can now come and interact with each one of them very weakly and collect information from all of them, and then indeed I will find that sigma x plus sigma y for each one of them, or the sum. If I do this weak measurement, I take the sum of sigma x n plus sigma y n divided by n. Take the sum of all these things. I measure this sum weakly, then I find that this is equal to 2n divided by n, as if indeed each one of these particles contributed one from here and one from there. This is the first exciting answer from learning to do measurement that don't disturb. So if I do measurement that don't disturb, I can find completely new rich phenomena in the time in between two measurements. And in fact, I can prove the following thing. Suppose you look at an example of weak measurement or any weak interaction. So I start with the state psi 1 and also some measuring device which I will describe by phi. Then I want to show an interaction of the type of von Neumann, for example, which is the simplest example to think about. I will write here a coupling which is e to I q times A times very weak parameter. This is an example where, due to the interaction between the two of them, I made this particle, which I call, this particle has coordinates q and pq, I make this particle change its momentum because it's a translation of momentum by an amount that depends on epsilon, on A and very small epsilon. And the question is now, if I do a post-selection on this particle with psi 2, what will be the momentum shift of this measuring device? So since this is very small, I can write it to, I can expand it to first order and write that thing between psi 2 and psi 1 and see what dependence will be left on q. So that is very, if I take now this thing, I see that I can write it as psi 2 times psi 1 times 1 plus iq epsilon times this very interesting combination. I will write it down. I multiply here by psi 2 a psi 1 divided by psi 2 psi 1. This is what I called a weak. So I define a weak to be a new quantity, very general in importance, that has a property that depends on the thing that I measure A and on the two boundary conditions, on the two vectors, psi 2 and psi 1. And I claim now that if I have a pre-post selection and I do weak measurement, this is the time of observable, of disturbance that will happen to any system. It happens in measurement, it happens when I have weak interaction, weak coupling between two systems. It's a general new kind of physical system, a physical property, they're called weak value, that will appear in general when you have both pre and post selection. Now, this thing has many interesting features. First thing is that if either psi 1 or psi 2 is an eigenvector of A, then the weak value will be the same as the eigenvalue. If psi 2 is equal to psi 1, then the weak value will be the average. So the two usual things that we are connecting with operators on states, namely averages and eigenvalues, they are special cases of this quantity. But this quantity has much richer things in it. First of all, if we look, for example, on A that is bounded, this A weak can be completely outside that range, because if psi 2 times psi 1 is very small, I can get a value that's much bigger than any of the eigenvalues. And in fact, this is being now used in many, many laboratories in the world to do a kind of amplification experiment where by choosing out of the ensemble a very small part of it by this pre and post selection, then the small part that is being chosen have a deflection or have an effect which is much bigger because of that small denominator, and that helps to see things that were too small to be seen up to now. Another very interesting thing about this variable is that it can be complex. It can be purely imaginary, very easily. What we mean to say that I can measure a quantity that is imaginary? How many time do I have?
15 minutes.
How many?
15.
Oh, very good. So, okay, so what does it mean that I measure something imaginary? In classical physics, it certainly doesn't have any meaning at all. Let's see if we can give it a meaning quantum mechanically. So suppose somebody tells me, look, I have a particle that has a momentum p. Quantum mechanics is described in the momentum representation by a function of p. This is the amplitude to get a momentum p. And now suppose I tell him that I have put on the particle an imaginary force for a finite time t. So then I know that the momentum, if it follows the usual rule, the momentum p of t will be p of 0 plus I times f0 times c. The force was I times f0, so that is how it should change. Now classically it will have no meaning, because it will tell you that you started with a velocity and you went up to an imaginary velocity, and therefore you immediately leave the space. But quantum mechanically, I look carefully and see, hey, it does have a meaning. If I look at psi of p plus I, say p0, some imaginary part, this is still in general in the Hilbert space. For example, if I look at a Gaussian, e to the minus p square over 2, and I say it goes to e to the minus p plus I p0 square over 2, then the interpretation of this will be, in fact, that I did not change the probability to find the given p, but I changed the probability to find x. Because e to the I p0 times p is a translation in x, not in p. So that means that in quantum mechanics I can give an interpretation. I add imaginary momentum to a particle. What I do, I change indeed this momentum by imaginary value, but it shows itself in the laboratory by actually changing the position of the particle. And experiments where you measure weak values now are also being done in many different places. Now let me show you some really other interesting consequences of looking in this new way. The first one is an example that I call the 3-box example. You have a particle that started initially in the state psi 1 plus psi 2 plus psi 3 divided by square root of 3. That means that the particle had equal probability, 1/3, to be in each one of these boxes. This was the state at time t1. At time t2, I make another experiment and I find the particle to be in the state psi 1 plus psi 2 minus psi 3. Since this state is not orthogonal to that state, I can find that state as a final state. I ask now, if I know that these are the boundary conditions, what would happen if I were to look at the particle in the time in between? For example, suppose I would open only this box and look whether the particle is there or not. Then I claim I must have found the particle there, because if I did not find the particle there, the state that will be left here will be psi 2 plus psi 3. The state that we'll find here is psi 2 minus psi 3. These are orthogonal to each other, so that can happen. So therefore, if I open this box, look whether the particle is there or not, I know that if I have this boundary condition, I must find the particle there with certainty. But if instead I would have opened this box, again I would have to find the particle there with certainty. Right? Because again, if I don't find the particle here, I will have here the state psi 1 plus psi 3. Here we have the state psi 1 minus psi 3. Again, they are orthogonal to each other, so this is impossible. So now, if I use usual quantum mechanics, people tell me, okay, what is this noise? I hear some ringing. Maybe it's... Okay. People in quantum mechanics will tell me, don't speak about things that you don't measure. Tell us what you are going to measure. If you are going to measure here, okay, it's not surprising, you find the particle there. But if you open both of them, you will never find both of them there, because these measurements disturb each other. Even though they are commuting, they disturb the boundary condition. So, to say that both the particles here and here doesn't make sense. But nevertheless, if I do weak measurement, they don't disturb the system. Maybe if I have an ensemble of such cases, I will find now that there are n particles here, there are n particles here. I make it up to an approximation of square root of n, so it's a weak measurement that interacts very weakly with each one of them. And then what do I find here? The answer here is that because the sum of the particles in the 3 boxes is n, then the number of particles here must be minus n. Now, what does it mean to find minus n particles? Doesn't make sense. But we have to think in which way we do the measurement. When we do weak measurement, we always look how this system affects another system. Suppose this system was a charge system, and if we have here n charges, then if we put a test particle here, we expect that instead of seeing if these charges are negative and this is negative, because there is a minus n here, we will expect it to be attracted to those instead of repelling. So the negative number simply tells us there are n particles here, when we do weak measurement, that have exactly the opposite properties of normal particles. They have the opposite charge, they have opposite mass, they will introduce the opposite gravitational field, etc. So we already learned that there is a meaning in quantum mechanics to extend the concept of particles in the sense that if we do weak measurement and we do pre and post selection, this is a post selection, I have only 5 minutes by post selection, okay. It's coming back to me now. Sorry? Can't hear you.
Opposite mass.
No?
Opposite mass.
Ah, yeah, of course. So I'm saying that if those particles behave exactly as if they have negative mass, if I put your normal test particle with positive mass, this test particle will be, instead of attracting that gravitational field, will act in the opposite direction to deal the gravitational field, so it will make this particle move this way. Okay? Now, but there are even more interesting things that can be done. Okay, let me tell you one more important thing. Once you come with new concept, it doesn't only let you prepare you to do all kinds of new experiments and to think about new things that can be done with user theory. It can also suggest to you a way to generalize the theory in directions that you did not expect before. Up to now, I said that the two boundary conditions are dictated by what I, an experimenter, do to find this boundary condition, this boundary condition. But in principle, since it looks so natural now to think about a quantum system described by two boundary conditions, the question is it feasible that our whole universe, which is after all one big quantum state, people always talk about the whole universe starting at the beginning as being a quantum state, so is it possible for our whole universe that instead of just an initial boundary condition, also a final boundary condition that is different from the one that will propagate from here to here? What will be the consequence of that? That already is a generalization. Up to now, all the predictions I talked about, I could get from the use of quantum mechanics. But now, since I'm not God, and I can't sit out of the universe and make a boundary condition, so I can ask the question by doing experiments. Now, can I find whether the universe has two boundary conditions or only one? So far, all the experiments that we've done in quantum mechanics were consistent with having only one boundary condition. But, or another boundary condition that is equivalent to saying that here we post-selected the same state as the initial one. But hopefully, or at least we should anticipate the possibility that at a range of experiments that have not been done, for example, experiments at very high energies, ultra high energies, Planck scale energies, or any other reasons where we did not do experiments so far of any kind, we should at least keep an open mind to look whether we have some hints to see that indeed our universe has two boundary conditions rather than one. And this is a very interesting kind of question to investigate. And I will finish just by telling you something like a funny story, but it's a true consequence of quantum mechanics. The story has to do with the thing that is described in Alice in Wonderland. How many of you read Alice in Wonderland? Most of you, I hope. In Alice in Wonderland, Alice meets a cat, Cheshire cat. And she starts to talk to the cat, and eventually the cat gets mad with her and decides to disappear. But when he disappears in a very funny way. First the tail disappears, first the body disappears, finally the face disappears, and the only thing that is left is the smile of the cat. So Alice is saying, my God, I've certainly seen a cat without a smile, but I've never seen a smile without a cat. What on earth could it mean? Well, until quantum mechanics, nobody knew what it could mean. But quantum mechanics teaches us what it can mean. Let me show you what quantum mechanics teaches us. In fact, I will not do it with cats, but I will do it with microscopic particles because we don't know yet how to interfere, for example, dead cat and live cat like Schrödinger wanted. But I will show you what it means for quantum particles. I can prove it to you and leave it to you as a home exercise that I can start with a particle, quantum particle, say a spin-half particle, that sits in two boxes. and the particle has a spin half. So for example, I start the particle initially with equal probability of being here and here, and with the spin being in the x direction. So the initial state is psi 1 plus psi 2 times the state sigma x equal to plus 1. Then I do a post-selection on the particle, and I find the state that is psi 1 with sigma x equal to plus 1, plus 1 half psi 1 over square root of 2, psi 2 with sigma x equal to minus 1. Then I can show that with these two boundary conditions, if I have many, many such particles, I will find that all the charge of the particle sits here, all the mass of the particle sits here, but their magnetic moment sits here, as if I was able to separate the spin from the particle. And I can do this with all kinds of properties. I can take an atom that has two levels, separate the energy of the atom from the atom itself, separate the polarization of a photon from the photon itself, and separate the cat smile from the cat itself. I have just to decide what is an anti-smile. Maybe that kind of thing, I'm not sure. Thank you.
Question.
Yes, there is some.
There is.
Oh, do it, okay.
What I don't understand is what is the difference between weak measurement and the following observation? If you have n states that are different, but you're guaranteed that they're equal to themselves, you have n
N copies, yeah.
n copies of the same state, then you know that for every two states that are different, n copies of the first will be almost orthogonal to n copies of the rest.
Right.
So you know that there exists.
You know that the principle
for
exists.
Neumann measurement.
That's right.
So what you're suggesting is basically a local measurement. Your weak measurement is performing this von Neumann measurement, but in a local way. Right?
Yeah.
So does it add anything to thinking about it in this way, or
no. The point is that first of all, indeed, that if you can do that thing in time. For example, you can take a state, prepare it at a given time, then prepare it again another time for the same particle n times, right? And then you can discuss this weak measurement that I'm discussing as a function of time. Although at any time we have just one particle, because we tested at any n times that the state was the same, then we can do this weak measurement and find what is the state. Okay? So I agree that mathematically, this by itself is not new mathematically, but it's new in the sense that people did not see how to do this experiment in general. For example, if you ask, how do you see what is the wave function psi of x if you have many replicas? So the answer was that you come to each particle and measure very, very weakly whether it's in this location or not, and then sum up this experiment, this measurement. This is a new kind of experiment that people did not think in order to see interference phenomena. They always thought about looking at the position of each particle of appears and drawing from that. So I'm saying we can do an interference phenomena without disturbing the system, and then we can find, for example, each particle through which slit it went, and nevertheless find out that it showed the interference. This is a new thing.
So if I compare the optimal measurement, which is theoretically global, to this measurement, is this measurement the optimal thing in terms of information versus disturbance?
I think if you want to if you want to use local experiment that each particle happen in different time, then I think this is the optimal one, the addition one. If you have all the particles, if you're not allowed to make interaction between the measuring device here and the measuring device here that depend on particles, then I think you can prove this is the optimal one. That's a good question, yes.
So this is a naive question, but someone has to ask it. The emergence of the arrow of time, entropy, does this formalism help us deal with that in some way? Just the standard formalism is almost useless in dealing with this question in a
Wait, with what
fundamental
question?
sense. Where does the arrow of time emerge?
Why do you say that user formalism is... I know how to use user formalism with some very simple assumption about initial direction, initial states to show that the entropy evolution is meaningful. It's a well-defined thing, even user formalism. I don't have to look at this one. But then this argument we have to do in another place, okay?
It depends on if
Yeah.
you belong to the Church of the Greater Hilbert Space or not, of the
yeah,
entire
right.
universe.
I see what you mean, yeah. Okay, I don't belong to that.
I guess this is also naive. What about the EPR paradox? So,
The what?
what about the EPR paradox? I mean, Einstein and co-workers claim to prove that there cannot be quantum mechanics cannot fully describe reality, and
Well, this is a very good question, and I will be somewhat heretical, okay? Heretical. Heretical is a good word? Okay. When Bell proved his theorem, he said the following: look, if each particle, when it goes out from the pair, we know in advance which measurement we are going to make on it, then there will be no inequalities. It's trivial. Because the particle will have to be correlated only for that experiment that will be done in the future. But he said, we can't think of each particle knowing in advance what experiment we are going to make on it, because in that sense we have no free will. Because we can change our mind at the end which experiment we are going to do, and therefore the particle doesn't have a chance to know now which experiment we are going to do later. So in a sense, and Bell wrote about it, he believes strongly that in order to have free will, we must have the Bell's inequalities. Now, it turns out that this formalism that I propose, in a sense, let the particle have the cake and eat it, in a sense. Because the particle has now, from my language, the particle has the user state that we know, and another state that comes back from the future, which we don't know. But the particle knows it already. So in a sense, there's a new kind of hidden variable. It's a hidden variable that doesn't tell you the answer for all possible experiments. It tells you the answer only for that particular experiment that you're going to do. When you learn to think about this formalism, you see that you can replace the effect, the non-local effect of one particle or another particle that doesn't interact with it anymore, by another non-local effect in time, that the thing that's coming back from the future affects it, okay? You can show that with this thing, you can describe all the effects of entanglement in a way that replaces the non-locality in space with the non-locality in time, that I'm describing it. I for myself find it much more intuitive to say that the particle in the present can be affected by what will happen to it in the future, rather than to say the particle in the present is affected by another particle that never is going to interact with it, never any connection with it, and never does it affect it. Much easier for me to understand that the particle is going to be affected by a future on itself. I like it much better. And I think that eventually this will be the way to speak about quantum mechanics.
My question may have something to do with what Nadav asked. And can you do everything you did with density matrices instead of using just wave functions? Which
Yeah, people have done it all over the place, yes, definitely. That formula has been developed by many people, including in an article by myself and Benny Redley. I think you are writing something about it too. Yeah, it has been described. Yeah, it can be done, certainly.
Two questions. One.
I can't hear you.
One question.
Okay, one. Yes, okay, one.
A naive question or not a naive one?
Sorry, not.
Yeah?
So for weak measurements, you have ensemble of systems, so spins, so dimension 2 to n, and you have a priori huge information. You know what Gilbert space, what your state, is in two-dimensional space, in fact, instead of two-dimensional. You assume that all your spins are the same, the state of all your particles are the same.
I didn't hear, maybe somebody heard the question. You can explain the question to me?
No, it's not a question. It's not yet. For weak measurement, you have ensemble of spins.
Yeah.
Yeah. And you know before the measurement what all of the spins are in the same state. Like you know all in the same state. So the Gilbert space of an ensemble is 2 to power n, very huge dimension.
Yeah.
But you assume a priori what your state in this ensemble is restricted to two-dimensional space.
No, it doesn't.
Yeah, because all spins are parallel. Yeah, so you assume what the state is restricted. So before the measurement, you have huge a priori amount of information.
Yeah. Okay.
So it's
In
this case, it is
you're completely right.
Get,
You're completely right.
Sorry.
Yeah, but the whole idea now, when we discuss usually an ensemble,
Yeah.
in order to check quantum mechanics, we already assume that all the n particles have the same state. Otherwise, we will never be able to check any result of quantum mechanics. So I assume something more, that I have two information like that.
Sorry, what you assume?
I assume they have one ensemble for the pre-state and another ensemble for the post-state, but all of them are the same state. Yes.
Yeah. So you have, and you cannot apply to this scheme to single spin because of non-cloning theorem. If you have unknown state, you cannot duplicate it, so you cannot create such ensemble. So you have a priori huge information, and like if you have single spin, if you prepare somehow state along sigma z, and you know, when you don't need to do any measurements, you know your results without any measurements. So you have quantum not disturbed measurement. So what is non-trivial here? It seems the scheme seems in the sense trivial. You just have huge amount of a priori information. And
I have a suggestion. It's too complicated. Maybe we can talk about it in the corridor, because I'm not sure I understand what you're asking.
Yeah. Okay. Last question, Sander.
Yes, Yakir, you were talking about post-selected state of the universe,
Right.
perhaps. Could you explain an experiment that might be able to see? Because all the idea of pre- and post-selection is that you do not destroy causality, hence you cannot know about the future.
That's right.
So how would you be able to know if the universe is post-selected or not?
Well, so if suppose, for example, that I will find a particular galaxy in the universe that has a magnetic field or magnetic moment that's much bigger than the one that we can explain from all its initial, from all the constituents, okay? Then I can show that if this galaxy will have a pre-selection of all its spins in one direction and a post-selection of all its spins in another direction, then it will explain why it has this magnetic moment. Now it will violate causality because nobody can come and change all these spins. I mean, by experiment you can change only an individual number of spins. You're talking about spins that are 10 to the 30 or 40. Nobody can do experiments that will check causality here. So when we discuss individual quantum systems, it's trivial to say that if the thing that comes from the future will show me something in the present, then it will violate causality because I can change that condition. But when I speak about cosmological things, cosmological measurements of electromagnetic field, gravitational field, that thing is a quick measurement and it doesn't violate causality because there is no way that I can change the boundary condition in the future.
Yeah, but it's still far more likely that you see that huge magnetic field by mistake and not because it is post-selected.
No. If that is not true, because my chance of seeing it at all is zero. So if I see it, the only explanation I can give to it is that there is a true post-selection. Otherwise, I would never be able to see it.
Okay, let's thank Yakir again.